This is Concept E classes, and today we'll deal with Chapter 3 of Class 9 Science, Atoms and Molecules. We'll be covering this chapter in two parts. In this video, we'll deal with Part 1. Here we'll see the laws of chemical combination, then we'll see what is an atom, we'll study more about atomic mass and all. Then we'll see what is a molecule, we'll also see what is an ion. The next two topics we'll be discussing in Part 2. So let's begin this video. So first let's see an introduction of atoms and molecules. How did these atoms came into being, who considered this and all. So in the previous chapters we understood that everything around us is made up of matter. What is matter? Anything that occupies space and has mass is termed as matter. So the ancient people, especially the Indian and Greek philosophers, they always wondered what this matter was made up of, or how did matter form. And this idea of divisibility of matter, what do you mean by divisibility? That is, a matter can be divided. That idea was actually considered long back in India, and around 500 BC many Indian philosophers like Maharshi Kanand and Pakuda Katyama, they put forward this idea of divisibility. Maharshi Kanand actually he suggested that if we keep on dividing matter, according to him he termed it as padarth, we shall get smaller and smaller particles, and then there will be a stage that these particles cannot be divided further, and he named such particles as Paramanu. Similarly, Pakuda Katyama, he also said that these particles, they normally exist in a combined form, which can give various forms of matter. That is, they do not exist independently, but they combine to form different forms of matter. That was what Pakuda Katyama also suggested. And it was around the same era, ancient Greek philosophers like Democritus or Leucippus, they also had some suggestions. They suggested that just like how Maharshi Kanand suggested, Democritus and Leucippus also suggested that if we keep on dividing matter, a stage will come when the matters cannot be divided further. And Democritus called these indivisible particles as atoms. What do you mean by indivisible? It is a stage where it cannot be divided again. Okay, so Democritus named these indivisible particles as atoms. Now all this was based on philosophical considerations till 18th century. There were no experimental work, only based on philosophies. And by the end of 18th century, the scientists started to recognize the difference between elements and compounds, and they naturally became interested in finding out how the elements combine, what happens when they combine sometimes chemical reaction takes place and all. Then later, Antony L. Lavoisier, he laid the foundation of chemical sciences by establishing two important laws of chemical combination. So Antony L. Lavoisier, he brought two laws that are obeyed by all chemical reactions. Okay, so let's see about these laws. Laws of chemical combination. So these laws of chemical combination was established after much experimentation by Lavoisier and Joseph L. Proust. So the two laws are law of conservation of mass and law of constant proportions. Law of conservation of mass. The law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. So this law states that the mass can neither be created nor destroyed in the chemical reaction. It remains the same. Let's take an example. Here we take 32 grams of sulfur and 56 grams of iron. Okay, so these are the reactants. So we combine them and then we heat them. So when we heat this mixture, a chemical reaction takes place. Now what was a chemical reaction? It is a process by which a new product is formed. We have explained what a chemical reaction is in the previous chapter. So if you have any doubt, just refer that slides. So here when we heat this mixture, a chemical reaction takes place and we get a new product, which is iron sulfide. Now if we take the mass of these two reactants, say for sulfur we took 32 grams and iron 56 grams, so we get a total of 88 grams of reactants. And here if we consider the mass of this product, it is 88 gram. So here in this chemical reaction, the total mass of reactants is equal to the total mass of the product. So here there is no change in the mass. The mass is the same. Hence the law of conservation of mass is satisfied here. Okay, so let's understand this law of conservation of mass through another activity. Take one of the following sets of X and Y chemicals. Either take copper sulfate or sodium carbonate or barium chloride with sodium sulfate and prepare separately a 5% solution of any of these substances listed under X and Y, each in 10 ml in water. Now take a little amount of Y solution in a conical flask and some solution of X in ignition tube. So let's say we'll take sodium sulfate in this conical flask and barium chloride in this ignition tube. Now hang the ignition tube in the flask carefully, just as shown in the figure, and see that the solution do not get mixed. Put a cork in the flask. Now weigh the flask with its contents carefully. Now what to do? Tilt and swivel the flask so that the solution gets mixed. Weigh again. What happens in the reaction flask? Let's see. So here first we hang the ignition tube in the flask, and when we weighed the contents, there was no change in the mass, 100 grams. Then we swilled the flask and tilted it, and hence the solution mixed, and hence a chemical reaction took place. So here it was barium chloride and in Y it was sodium sulfate. So we got barium sulfate. A chemical reaction took place and a white precipitate was formed. Okay, so here after this chemical reaction, when we checked the mass of the solution, it also remained the same. So here, even though we heat the solution separately or even after mixing them and heating them, there is no change in the mass. So the law of conservation of mass is obeyed here. So what was the law of conservation of mass? It stated that the masses can neither be created nor destroyed in a chemical reaction. It always remains the same. Now let's see the law of constant proportion. Now Lavoisier and his colleagues noted that many compounds were made up of two or more elements, and each such same element in the same proportion irrespective of where it came from or who prepared it. Say for example the compound water. Here the compound of water is made up of two elements, which is hydrogen and oxygen. Okay, so whatever the source of water may be, if you take the water from a lake or from the ocean or from a river, it always contains two atoms of hydrogen and one atom of oxygen. Okay, it contains the same elements, and the ratio of the mass of hydrogen to the mass of oxygen would also remain the same. It is always remains 1:8. Now how do we get this ratio 1:8? It is because the mass of hydrogen atom is 1, the mass of oxygen atom is 16. Okay, now we know that in a water molecule we have two hydrogen atoms, so 1 into 2, which is equal to 2. Oxygen, the mass is 16. The ratio of mass of hydrogen to oxygen is 2 by 16, which is equal to 1:8. So the ratio is 1:8. Thus, if 9 grams of water, take it from any source, if it is decomposed, we'll always get 1 gram of hydrogen and 8 grams of oxygen. Okay, similarly, in the case of ammonia, NH3, the mass of nitrogen is 14, the mass of hydrogen is 1, but we have 3 atoms here, so 3U. So the proportion is 14:3. If you take ammonia from any source, always the elements would be same. Nitrogen and hydrogen will be the atoms, and the ratio would be 14:3. So this led to the law of constant proportion, which is also known as law of definite proportion. So this law, which is stated by Proust, is that in a chemical substance, the elements are always present in a definite proportion by mass. Or in simple words, in a pure chemical substance, it consists of the same elements combined together in a fixed proportion by mass. That is the law of constant proportion. So the next problem faced by the scientist was to give an appropriate explanation for this laws. So the British chemist John Dalton, he provided the basic theory about the nature of matter. Dalton picked up the idea of divisibility of matter. He took the name atoms as given by the Greek Democritus and said that the atoms are the smallest particles of matter. His theory was also based on the law of chemical combination, which was suggested by Antony Lavoisier and Proust. Okay, so Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite proportions. If you want to know more about this Dalton theory, message me in the comment section. I'll give you a separate video on this Dalton's atomic theory. Now, according to Dalton's atomic theory, all the matter, whether an element or a compound or a mixture, is composed of small particles called as atoms. Now, let's see the postulates of this theory. All matter is made up of very tiny particles called as atoms, which participate in a chemical reaction. Now, these atoms are indivisible particles, that is, they cannot be divided, they cannot be created or destroyed in a chemical reaction. Now, atoms of given elements are identical in mass and chemical properties, because in an element all the atoms are same in mass as well as chemical properties. Atoms of different elements have different masses and different chemical properties. We'll study more about this in the following slides. Now, atoms, they combine in the ratio of small whole numbers to form compounds. Just now we saw, right, H2O, two atoms of hydrogen and one atom of oxygen, and so these atoms combine to form a water molecule, right? And the relative number and kinds of atoms are constant in a given compound. Just as we saw in the previous slide, whatever the source of water is, the water molecule will always consist of two atoms of hydrogen and one atom of oxygen. So they are constant. So these are the main postulates of Dalton's atomic theory. Now let's see atoms. Now, what is an atom? Atom is the smallest unit of an element, or the smallest unit of matter is termed as atom. Now, this is the structure of an atom. We have protons, neutrons, and electrons. We'll study more about this structure of an atom in the next chapter. Okay. Now, the building blocks of all matter are atoms. You might have observed how a mason makes a wall, right, using bricks. Then from this wall a collection of rooms is formed, then from that rooms a building is formed. Similarly, the building blocks of all matter are atoms. Now, how big are the atom? Actually, atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms, when stacked, would make a layer barely as thick as a sheet of a paper. Now, the atomic radius, or the radius of an atom, is measured in nanometers. 1 nanometer, see, 1 by 10 raised to 9 meter is 1 nanometer. It's very small. So if it's so small, why should we care about them? That might be the next question. That is because even though we are not able to see them, they are there, and it's constantly affecting whatever we do. Now, through modern techniques, we can now produce a magnified images of surface of elements showing atoms. See here, this is an image of the surface of silicons, and through that we can see atoms. Now let's see the symbols of atoms of different elements. Now, Dalton was the first scientist to use the symbols for elements. So these were actually some of the symbols for some elements as proposed by Dalton. When he used the symbol for an element, he also meant a definite quantity of that element, that is, one atom of that element. Later, Berzelius, he suggested that the symbols of the elements can be made from one or two letters of the name of the element. Now, in the beginning, the names of the element were derived from the name of the place they were found for the first time. For example, name copper. It was taken from the place Cyprus. Similarly, some names were taken from specific colors. For example, gold. It was taken from the English word meaning yellow. But now, IUPAC, the International Union of Pure and Applied Chemistry, it is an international scientific organization. This organization approves the names of elements, symbols, and units. Many of the symbols nowadays are first one or two letters of the element's name in English. For example, hydrogen, H, aluminium, Al, cobalt, Co. And if you notice these examples, we can see that the first letter of the symbol is always written in uppercase, capital letter, and the second letter is small letter. See, neon, Ne, beryllium, Be, lithium, Li, helium, He. Now, symbols of some elements are formed from the first letter of the name, and a letter appearing later in the name. For example, chlorine, Cl, zinc, Zn, etc. Now, other symbols have been taken from the names of elements in Latin or German or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is Na from natrium. Potassium is K from kalium. So these symbols have taken from the names of the elements in Latin, German or Greek. Therefore, each element has a name and a unique chemical symbol. See, these are some of the symbols of element. Aluminium Al, argon Ar, barium Ba, boron B, bromine Br, calcium Ca, carbon C, chlorine Cl, cobalt Co, copper Cu, fluorine F, gold Au, hydrogen H, iodine I, iron Fe, lead Pb, magnesium Mg, neon Ne, nitrogen N, oxygen O, potassium K, silicon Si, silver Ag, sodium Na, sulfur S, uranium U, zinc Zn. So these are some of the symbols of elements. With the passage of time, you will understand it automatically. Okay, what all are the symbols? Now let's see about atomic mass. Atomic mass was one of the most remarkable concepts that Dalton proposed. According to Dalton, each element had a characteristic atomic mass. See, for oxygen, the atomic mass is 15.999. Whole number wise, we say that the atomic mass of oxygen is 16. Now, what is this atomic mass? Atomic mass is the mass of a single atom of a chemical element. The mass of an atom is the atomic mass. So it actually includes the masses of protons, neutrons and electrons. Say for example, carbon atom. The atomic mass is 12. Number of protons plus number of neutrons gives atomic mass is 12. Here usually we don't take the mass of an electron to calculate the atomic mass because the electrons are very small. Hence the mass of these electrons are usually neglected. Now atomic mass can be expressed in grams as well. So the Dalton theory, it explained the law of constant proportion so well that the scientists were very interested to measure the atomic mass of an atom. But to determine the mass of an individual atom was very hard because atoms are very small. Hence, relative atomic masses were determined using the law of chemical combination and how the compounds were formed. Relative masses means the average relative mass of an atom. Take for example, carbon monoxide, the compound. It is formed by carbon and oxygen. So 3 grams of carbon combines with 4 grams of oxygen to form carbon monoxide. In other words, the carbon combines with 4 by 3 times its mass of oxygen. The atomic mass unit AMU, but according to the latest IUPAC recommendation, it is now written as U, which means unified mass. It is as equal to the mass of one carbon atom. One atomic mass unit is a mass unit equal to exactly 1/12 of the mass of one carbon atom. That is, if the mass of a carbon atom is 1.992 into 10 raised to minus 23 gram, one atomic mass unit or 1 AMU is equal to 1/12 of a mass of one carbon atom. Hence, the mass of carbon atom 1.992 into 10 raised to minus 23 grams divided by 12, that is equal to 1.66 into 10 raised to minus 24 grams. So 1 AMU is equal to 1.66 into 10 raised to minus 24 grams. Hence, we could assign a carbon has an atomic mass of 1.0 U because 12 divided by 12 is equal to 0. And for an oxygen, the atomic mass is 15.99, or we could use as a whole number 16. 16 divided by 12, we'll get 1.33 U. Scientists initially took 1 by 16 of the mass of an atom of oxygen as a standard unit. However, in 1961, for a universally accepted atomic mass unit, carbon-12 isotope was chosen as the standard reference for measuring the atomic masses of different elements. The relative atomic mass of all elements have been found with respect to an atom of carbon-12. So as we said earlier, the relative atomic mass of an atom of an element is defined as the average mass of an atom. Okay. Now some of the atomic masses of some elements are given here. For hydrogen, the atomic mass is 1, carbon 12, nitrogen 14, oxygen 16, sodium 23, magnesium 24, Sulfur, the atomic mass is 32, chlorine it is 35.5, and calcium it is 40. Now, how do these atoms exist? Atoms of most elements are not able to exist independently. Atoms forms molecules or ions. These molecules or ions, they aggregate in large number to form matter that we can see, feel or touch. Say for example here, see these hydrogen and oxygen, they combine together to form water. See, so these atoms, they combine to form molecules, and the molecules, they combine to form matter that we can see, feel or even touch. Now let's see about molecules. What is a molecule? A group of two or more atoms that are chemically bonded together is called as molecules, and these atoms are tightly held together by attractive forces. Say for example water, H2O, ammonia, NH3, carbon dioxide, CO2, CH4 is methane. So here all two or more atoms are chemically bonded together by attractive forces. So these are called as molecules. A molecule can be defined as the smallest particle of an element that can exist independently. Okay, and these molecules show all the properties of that substance as well. Now atoms of the same element or different elements can join together to form molecules. Now let's see the molecules of element. Now the molecules of an element are composed of the same types of atom. For example hydrogen, see H2, same types of atoms. Nitrogen N2, oxygen O2, OO. See, so molecules of an element are composed by the same type of atoms. Molecules of many elements are made up of only one atom of that element. For example, neon, argon, helium, they have only one atom of that element. In case of non-metals, say for example the molecule of oxygen, if it consists of two atoms of oxygen, it is called as diatomic molecule. See, oxygen. If three atoms of oxygen unite into a molecule, we get ozone, O3. Now the number of atoms constituting a molecule is known as atomicity. The number of atoms constituting a molecule is known as atomicity. For example, we say the atomicity of oxygen is 2. The atomicity of ozone is 3. Okay, so the number of atoms which the molecule consists is termed as atomicity. Some metals and other elements consist of a very large and indefinite number of atoms bonded together. For example, carbon. Now in this table we have given some atomicity of some elements, mostly non-metals. Argon, it is monoatomic, that it consists of only one atom. Helium, it's also consists of only one atom. Oxygen, it's diatomic, it consists of two atoms of oxygen. Hydrogen, diatomic. Nitrogen, diatomic. Chlorine, diatomic. Phosphorus, it is tetraatomic, that is it contains 4 atoms. Sulfur, it is polyatomic, it consists of 8 atoms. Molecules of compounds. Now atoms of different elements, they join together in definite proportions to form molecules of compounds. For example, here in the molecule of water we have 2 atoms of hydrogen and 1 atom of oxygen. 1 atom of hydrogen combined with 1 atom of chlorine to form molecule of hydrogen chloride. Now here 2 atoms of hydrogen, they combine with 1 molecule of water in a fixed proportion, right? So in a particular ratio. So let's say the ratio by the number of atoms for a water molecule can be found as follows. So we know that in a water molecule we have 2 elements, hydrogen and oxygen. We already know the ratio by mass is 1:8, right? So if we know the ratio by mass, and if we have the atomic mass, we are able to find the ratio in the number of atoms. Okay, so the atomic mass of hydrogen is 1, the atomic mass of oxygen is 16. Okay, so mass ratio by atomic mass of hydrogen is 1 by divided by 1, which is equal to 1, and 8 by 16 is equal to 1 by 2. And by using the highest common factor, by multiplying it with 2, we get 2:1. Hence the ratio by the number of atoms for water is 2:1. So 2 atoms of hydrogen combined with 1 atom of oxygen to form 1 molecule of water. So atoms of different elements, they form together in definite proportion to form molecules of compound. Now let's see about ions. Compounds composed of metals and nonmetals contain charged species. It contains atoms which have charge. These charged species are known as ions. Ions may consist of a single charged atom or a group of atoms that have a net charge on them. Or in simple words, an electrically charged atom or a group of atoms are called as ions. The ions can be either negatively charged or positively charged. A negatively charged ion is called as an anion and a positively charged ion is called as a cation. Take an example of NaCl. Its constituent particles are positively charged sodium ions, Na, plus and negatively charged chloride ions, which is Cl negative. So here cation is Na plus and the anions are chlorine ions. Okay. Now a group of atoms carrying a charge is called as a polyatomic ion. A polyatomic ion is a group of atoms carrying charge. So these are some of the ionic compounds. We have calcium oxide. The constituent elements are calcium and oxygen. Here the cations are calcium Ca2 plus and anions are oxygen O2 minus. And the ratio by mass is 5:2. And here we have magnesium sulfide. Here the cations are magnesium Mg2 plus and anions are sulfur S2 minus. Then we have sodium chloride. Sodium are the cations here, cation ions, and chlorine ions are the anions. So that's all for part 1 of chapter 3. Tune in soon for the next session. Thank you so much. May God bless you all. Stay safe and take care. Bye bye.